Hello guys, welcome back to our channel. Today we are going to see SIPO. SIPO is nothing but the serial in parallel out shift register. In the previous video, we discussed about the serial in serial out shift register with its Verilog code. You can also check out this video which is shown in the I button which is at the top right corner. Okay, now we will discuss today SIPO, serial in parallel out shift register. The major difference between the serial out shift register and the serial in parallel shift register is here we will give the input as a serial manner and we will get the output as a parallel. That means in the serial in serial, that means SISO, the input will be given bit by bit to the bit by bit Q3, Q2, Q1, Q0, and finally here we get the serial output for the SISO. Here also we will get the bit by bit. Okay, in the serial in parallel out manner, the taking of outputs will be different. That means here directly the outputs will be taken at their states. Okay, simply if you feeding the four inputs, suppose if we applying the four inputs, then four clock cycles are required to feed the bits into this shift register, and only one clock cycle is required to get all the bits to the output. Okay, you can more understand easily when we are discussing the Verilog code. Okay, so before that we will briefly see the operation of this circuit. Before going to the operation, we will just recall our D flip-flop truth table. So in D flip-flop we have clock, D and the Q, right? So when the clock is 0, wherever the output, that means if it is 1 or 0, irrespective of the output, the Q will be present in memory state or it is in the previous state. Okay, if clock is 1, if D is 1, then output will be 1. If clock is 1, D is 0, then output will be 0. Simply when the clock is 0, the flip-flop will be inactive and it is considered the data of the previous state. And if the clock is 1, irrespective of the, whatever the input of the D, the output will be same as the input. Okay, now we will see the operation. I will draw some clock cycles. Okay, I am considering some few clock cycles, and I am selecting a positive edge because we are designing as flip-flop as a positive edge. If you want to make it as a negative edge trigger, so you just add a inverter here. Okay, I am using the positive edge. So only when the positive edge signal is received, then only the output will be respond, otherwise the output will not be respond. Okay, the inputs are fed in the serial manner, right? So initially the Q3 will respond will 1 and it will continue the next clock cycle positive edge, and Q2 will be remain same, Q1 will be remain same, and Q0 will be remain same. Okay, next the Q3 will be follows the D, so it will be 0 and it will be shifted to the next. So here 1, here it will be continued, here it will be continued, and next clock cycle is 1, so 1 is there, so this state will be shifted to this, so 0, and here this state will be shifted to here. Now Q1 will be 1 and this state will be to the 0. Okay, next here 0, this state will be shifted here 1, and here 0, and here it will be 1. Now here the outputs will be directly come, that means here initially 1 0 0 0, then the output will be 1 0 0 0, and here 0 1 0 0, right? So 0 1 0 0, and here the output is 1 0 1 0, so output is 1 0 1 0, and here output is 0 1 0 1 0 1 0 1. In this way the input is feeding serially and the output will be coming as a parallel manner. So in this way the serial in parallel shift register will be work. Now we will see how to make the Verilog code for this serial in parallel shift register. Okay, Now we will start making the Verilog code for the serial in parallel out shift register. So for that I am creating the module with the name called SIPO. You can write you whatever you want and just writing the SIPO. Here we require some inputs. So inputs clock, reset and the serial input. Okay. Now we will require some output register, and it must be contains. We are designing a 4-bit shift register, right? So it has to store the 4 bits. So I'm writing the 3 is to 0 s naught will be nothing but the s naught 0, s naught 1, s naught 3, s naught 2. In this way there will be 4 positions will be created by using this command. Now I will select some other register to store the temporary values. 3 is to 0 temp. Now I am using the always command, always at the rate positive. That means the signal will be respond only to the positive edge of the clock signal. Now if reset is I, okay, if reset is equal to 1, then what will happen? The temporary register will be equal to 4 bit 0. You can write in this way, and I am ending this. If reset is not I, then initially the temp will be shifted to one time right, so that it will be right shift operation, right? Now at the temp position, temp MSB, here we considering the 4 positions, so it will be start from the 3 2 1 0. So at the third position the first input bit will be feeded to that position. So temp 3 is equal to SI. Now I am closing this. Here I will take the entire temp value to the S0 register. Already S0 will able to store the 4 bits. So it will directly take the 4 bits of the temp register, and finally end module. This is the design code for the serial in parallel shift register. Now we will create the test bench module DB. Your registers are nothing but the register clock, reset, and the serial input. And Y is nothing but 3 is to 0, which is S0. I'm extracting the inputs from the design code SIPO1. What are the inputs? Clock, reset, serial input, serial output. Sorry, you can also write as a parallel output. It will be convenient to you. Yeah, I will write that. I'm writing as a parallel output P0. Here also I will change it. Parallel. Now first I will give the clock signal, which will be work until and unless the all the test bench is completed. Okay, initially clock is 1. We'll let the some comments to display those values at the output after the test bench is fed. So what are the outputs here? Will present reset. Reset is equal to percentage B, which is used to represent the characters or votes. Clock equal to percentage B, and SI is equal to percentage B, what the input we are feeding, and what the output we are taking will be the P0B, which is just similar to the C language. Reset comma clock comma SA comma P0. Okay, I hope you are understanding. And I also write some dump file comments which will be able to show the output waveforms. By you seeing those, we can identify more about the circuit operation well. So dump as one, no forever command, so that it will be changed for every 10 or every 5 seconds. It's changed. It will be change its state. Now I'm ending this. Now I will give the main test bench initial begin. Initially I will give reset as a 1, and I will give SA as anything. I will 1 and it for 10 seconds. Now I will reset is equal to 0. Now I will give the inputs say equal to 1 for 10 seconds. I just copying this 1 0. I will give the sequence as a 1 0 1 0. Okay, now the test bench is completed. Now I'm closing this and module. Okay, now I will select the tool to run this. So I'm selecting the IQ 0.9.7 and I will select the open EP view. Now I will save this file. I'm writing the giving the name as SIPO and I will save this file. And here I will add some sequences for the better understanding. I will give just as a 0. Okay, I'm just copying it. Okay, I'm saving this file and I will run this. Yeah, here I'm getting some waveforms, right? So here you can observe that uh, initially the reset is high. So whatever the input is, the output will be in the previous state. There will be no previous states before the reset is high. So it is showing as a red mark. And after reset is 0, firstly the according to the inputs, the output will be adjusted. Here you can see that firstly 1010. Here you can better understand it. First 0 0 and next 1 and next 0 1 double 0 and next is 1 0 1 0 as we are according to our theory. So this is the SIPO. You can get this code through the GitHub, which link is provided in the description. If you have any doubts, please mention in the comment section. Thank you for watching this video. Stay tuned for the next one.